daredevil motorcyclist needs to achieve a speed of 110 km per hour before he reaches the ramp to safely complete the stunts. What is the shortest run-up he will need if the motorcycle accelerates uniformly at 15 meters per second squared from rest? First thing to notice is that the maximum velocity to be achieved by the motorcyclist is given in kilometers per hour. We need to first convert this into the SI unit of meters per second. So to do this, we know that 110 kilometers is equal to 110 times by 1,000 meters, and there will be 60 minutes in 1 hour and 60 seconds in 1 minute. So we'll have to divide this by 60 minutes in 1 hour and divide it again by 60 for 60 seconds in 1 minute to get to per second. This gives us a maximum speed of 30.56 meters per second. A quicker way of converting between kilometers per hour to meters per second is simply dividing 110 by 3.6. So we know the maximum velocity to be achieved is 30.56 meters per second, and the initial velocity of speed of the motorcyclist, given that he will be accelerating from rest, will be 0, and we know the acceleration of the motorcyclist will be 15 meters per second squared. Which of these three kinematic equations will help us determine the displacement of the motorcyclist during the acceleration? We'll use the third equation here. V squared equals to U squared plus 2AS. V squared is 30.56 squared. This is equal to the initial speed squared, which will be 0 squared, plus 2 multiplied by the acceleration, which is 15 meters per second squared, and then we'll multiply by s, which is the displacement. The value of s is 31.1 meters. So the motorcyclist will take 31.1 meters of run-up in order to accelerate from an initial speed of 0 meters per second to a maximum speed of 30.56 meters per second. A cyclist traveling at a constant velocity of 10 meters per second when they begin to decelerate at minus 1.5 meters per second squared. How many seconds will the cycle come to a stop? So for part A, our initial speed is 10 meters per second, and we want our final speed to be 0 because we want the cycle to come to a stop. And the acceleration is minus 1.5 meters per second squared. We want to find the time over which the cyclist takes to decelerate. So we use the first equation here because it has V, it has U, it has A, and most importantly, it gives us our time. So V equals to U plus AT. V will be 0, U is 10, plus the acceleration of minus 1.5 multiplied by time. The time here will be roughly 6.67 seconds. Alright, let's go through part B. What is the displacement of the cyclist at t equals to 8 seconds? So we're looking for displacement. We can use either the second or the third equation. The more appropriate kinematic equation will be the second one because we want to find the displacement. We have information on the initial speed, which is 10 meters per second. We have the time, which is 8 seconds, and also we know the acceleration, which is minus 1.5 meters per second squared. The other equation here is not as suitable because we don't know what the final speed or the velocity of the cyclist would be at 8 seconds. So S equals to UT plus half AT squared. S equals to 10 multiplied by 8 seconds plus half times by minus 1.5 for the acceleration and times by time squared, so 8 seconds squared. The answer for the displacement is 32 meters. So the cyclist is currently 32 meters in the positive direction from his origin. Alright, part C. What is the total distance traveled in the first 8 seconds? The difference between question part B and part C is part B is asking for displacement, whereas part C is asking for the total distance. Displacement is a vector quantity, which accounts for direction, whereas distance is a scalar quantity. It includes the total displacement regardless of the direction of travel. From part A of the question, we deduce that at t equals to 6.67 seconds, the velocity of the cyclist becomes 0 due to the deceleration of minus 1.5 meters per second squared from an initial speed of 10 meters per second. So in the first 6.67 seconds, the velocity decreases uniformly from 10 to 0 meters per second. What happens between 6.67 seconds and 8 seconds? In the second interval, as the cyclist continues to decelerate at minus 1.5 meters per second squared, the velocity will continue to decrease and hence it will become negative. So when t is between 6.67 to 8 seconds, the velocity will become negative. This indicates that the cyclist will start to travel in the negative direction. This has a very important implication on displacement and distance. When an object travels in the negative direction, it will start to decrease the displacement value, but at the same time, the distance will continue to increase. And that's because a negative velocity means that the cyclist is heading back to the starting point. It will slowly decrease the displacement or the position of the cyclist from the starting point. So in part B, the 32 meters that we calculated, this is the displacement. This already accounts for the fact that the cyclist has turned around and started traveling back to the starting point. To find distance for part C, we need to work out the distances traveled in the two intervals separately and then add them together because the cyclist is traveling in a different direction in each of these intervals. To find the displacement/distance in each interval, we can reuse the second kinematic equation. So S1, let's call that the displacement in interval 1, will be equal to 10 for the initial speed times by 6.67 plus half times by minus 1.5 times by 6.67 squared. And the displacement we get here is roughly 33.3 meters. That is the position of the cyclist from the starting point in the first 6.67 seconds. We can use the same equation for the second interval. In the second interval, the initial speed will be 0 because the second interval starts at t equal to 6.67 seconds and the velocity of the cyclist at this specific time is 0. So the initial speed here will be 0. The time in the second interval will be between 6.67 to 8 seconds. The difference between the two time points is approximately 1.37 seconds plus half times by the acceleration, which is still minus 1.5 meters per second squared, and we'll multiply by 1.37 squared here as well. The displacement that we get in the second part is minus 1.33 meters. The negative displacement here should make sense because in the second interval, like we already emphasized, the velocity of the cyclist is negative. It's heading towards the negative direction. And when you add them together, 33.3 minus 1.33, we should get back our total displacement of 32 meters that we calculate in part B. However, the question in part C is asking for the total distance, which is a scalar quantity. To find the distance traveled, we need to add the absolute value of both displacements. So the distance is equal to 33.3 plus the positive value of this displacement value, which is 1.33. So this gives us roughly an answer of 34.67 meters. That is the total distance traveled by the cyclist in the first 8 seconds. A sprinter runs 100 meters in 10.9 seconds. She accelerates uniformly and reaches the top speed of 3.7 seconds after the start and maintains the speed for the rest of the race. For this question, it's important to notice that the motion of the sprinter is split into two intervals. The first 3.7 seconds, the sprinter accelerates uniformly, and between the 3.7 seconds and the end of the race, which is 10.9 seconds, the sprinter will continue to move at constant speed without any further acceleration. So for the first part of the motion, we know that the initial speed will be 0, and the final speed is what we're trying to find. That's the top speed of the sprinter. And when the time taken is 3.7 seconds. We can use the second equation to derive an expression for this first interval. Let's call that S1. The displacement covered in the first interval is equal to 0 times by 3.7 plus half times by the acceleration, which we don't know. Let's call that A, times by 3.7 squared. So this simplifies into just half times by a times by 3.7 squared. The second interval is when the sprinter is moving at a constant speed without further acceleration. So the displacement covered in here will be the top speed achieved by the sprinter multiplied by the time. And the time here will be the difference between 10.9 minus 3.7 seconds, the remaining time of the race. So S2 is equal to 7.2 V. S1 is the displacement in the first part of the race, and S2 is the displacement of the second part of the race. The total displacement is 100 meters. So the value of S1 plus S2 should be equal to 100. So we know that 7.2 V plus a half A times by 3.7 squared, this should give us a value of 100. Now, we have an equation where we have two unknown variables, so we are not yet able to solve for the value of V, the top speed of the sprinter. This is where we can start looking at another kinematic equation to help us convert this equation into one unknown variable. So V equals U plus AT is very useful here because we know that V is the top speed, U is the initial speed of the athlete, which is 0 meters per second, plus the acceleration, which is also unknown, but the time is 3.7 seconds because we're told that the sprinter reaches the top speed 3.7 seconds after the starting point. So the time is 3.7 here. And A is equal to V divided by 3.7. Now, we can substitute this value into our equation. So 7.2 V plus half times by A, and A here is V divided by 3.7 times by 3.7 squared equals to 100. The 3.7 and the square here will cancel, and our simplified expression will be 7.2 V plus half times by 3.7 times by V equals to 100. 9.05 V equals to 100, and V is equal to 11.05 meters per second. A car begins to accelerate at 2 meters per second squared from an initial velocity of 10 meters per second. After 5 seconds of acceleration, the driver applies the brakes, causing the car to decelerate at 3 meters per second squared until it comes to a stop. How long does the car take to come to a complete stop after the brakes have applied? So to know the time taken for the car to come to a complete stop, we need to know what the initial velocity of the car was when the brakes were applied. There's two parts to this question. The first part of the question is when the car is accelerating at 2 meters per second squared. And the second part is when the brakes are applied, causing the car to decelerate at 3 meters per second squared. So we can approach this question by analyzing the two intervals. In the first part of the motion, we can use V equals to U plus AT to determine the final velocity of the car. V equals to U here is 10 meters per second plus 2 meters per second squared multiplied by 5 seconds. The final velocity we calculate here will be 20 meters per second. So the car is traveling at 20 meters per second after the first interval of acceleration. In the second interval, we can again use the same equation to find the time required to allow the car to come to a complete stop. The V in the second equation is the final speed after this interval. In other words, the final speed after the car has started to decelerate. So then this will be 0 because we want the car to come to a complete stop. The value of U, the initial speed, is the same value as the final speed of the first interval. So this will be 20 meters per second. And A is minus 3 meters per second squared because the car is decelerating. And time is what we're trying to calculate. T is equal to 6.67 seconds. So the car takes approximately 6.67 seconds to come to a complete stop. Part B, how far does the car travel during the entire motion? To analyze the distance traveled by the car, we need to work out the distances in each part of the motion, interval 1 and interval 2. The reason why we have to do this is because the acceleration of the car is different in each interval. To work out the displacement, we can use the second kinematic equation. Let's call that S1, the first interval, equals to ut plus half at squared. S1 is equal to the initial velocity of 10 meters per second The time in the first interval is 5 seconds plus half times by 2 for the acceleration times by 5 squared. The displacement covered in the first interval is 75 meters. Now we can do the same thing for the second interval, S2, equals a ut plus half at squared. The initial velocity of the second interval, like we emphasized, was 20. The time in the second interval was 6.67 seconds, as we calculated in part A, plus half times by A, which is minus 3 meters per second squared, times by 6.67 seconds squared. And the displacement in the second interval is 66.67 meters. So the total distance is the sum of the two values. Since both displacements are positive, we can simply just add them together. So the distance is equal to 75 plus 66.67, and this gives me an approximate answer of 142 meters. A boat is trying to cross the river that flows at 4 meters per second to the east. The boat has a velocity of 10 meters per second to the north relative to the water. What is the boat's velocity relative to the ground? So let's draw a diagram to better visualize this question. So we have a river. Let's call that north. Let's call that east. This is the water. This is the ground. So the water in the river flows to the east at 4 meters per second. And the boat, which is trying to cross the river, is moving north relative to the water at 10 meters per second. The velocity of the boat relative to the ground will also take into account the velocity of the water, because the water will be pushing the boat towards the east direction. To work out the net velocity, we need to use our vector diagrams. So we have the velocity of 4 meters per second to the east due to the river, and we'll also have the velocity of the boat relative to the water going north at 10 meters per second. We join the tail of one vector to the head of the other, and the resultant vector is the hypotenuse of this right angle triangle. This will be the velocity of the boat relative to the ground. So let's work it out here. The magnitude of this v value can be worked out using Pythagoras theorem. So this will be 4 squared plus 10 squared, everything square rooted. And the value of this is approximately 10.77 meters per second. For velocity, we need to provide a direction. The direction can be worked out by finding the angle between the horizontal vector and the hypotenuse, which is the velocity vector itself. So theta is equal to tangent inverse of the opposite side divided by the adjacent side. So 10 divided by 4. The angle here is about 68.2 degrees. So recall that the vertical vector here represents north, the horizontal vector here represents east. So my velocity of the boat relative to the ground is equal to 10.77 meters per second east, 68.2 degrees north. Okay, because this angle starts off from the horizontal vector, which is east, and goes towards the vertical vector, which is north. Alternatively, you can also describe the direction by finding the alternative angle here between the north vertical vector and the velocity of the boat relative to the ground. In which case, the angle will be north 21.8 degrees east. In either case, the directions are equivalent. If the river is 100 meters wide, how far downstream does the boat land from its starting point? So the distance between two ends of the river is 100 meters. This is what the boat needs to cross. However, as the river is flowing at 4 meters per second towards the east, by the time the boat reaches the other side of the river, it will end up somewhere over here. And this distance or displacement is what we are trying to calculate. For this scenario, it's important to understand that we have two dimensions. We have the boat heading in the north direction, which we can call that a vertical direction. And at the same time, the river is pushing the boat towards the east direction. We call that a horizontal direction. The two directions are perpendicular, so we should always analyze them separately. The time taken for the boat to cross the river is purely dependent on the boat's velocity relative to the water, which was 10 meters per second to the north. If the river is 100 meters wide and the boat travels at a constant velocity of 10 meters per second, then the time taken will be 100 meters divided by 10 meters per second, which will be 10 seconds. In the same amount of time of 10 seconds, the water in the river will be pushing the boat at 4 meters per second to the east. So the displacement caused by the flow of the water will be 4 meters per second multiplied by 10 seconds. So this will be 40 meters. The distance of the boat downstream from its starting point will be 40 meters to the east. Hey everyone, if you found this video helpful, smash that like button and don't forget to subscribe. Want even more? Become a Patreon member for early access to videos, exclusive Discord discussions about questions on chemistry and physics, and live preparation sessions for your exams. Don't forget to head over to our website for topic tests and practice exams to further improve your understanding and learning.